Um, Welcome to the Simon's Quantum Colloquium. So today we are following a slightly different format. Following last week's talk on quantum fault tolerance by Daniel Gottesman, today we have another talk on fault tolerance, or flag fault tolerance. And so following that, we'll have a panel, and we are really, it's great that we have a distinguished panel of John Martinez, John Presco, and Peter Shaw. So that'll be immediately following the colloquium, so in 1 hour. And then the plan is for the panel to go for half an hour, and then following that we'll be on Gather Town as usual, so for more in-depth discussions. So let's see, without further ado, let me introduce our speaker today, Rui Chao. So Rui is currently a postdoc at Duke University. He did his PhD with Ben Reichart, where he introduced, in his work with Ben, he introduced this notion of flag fault tolerance, which he'll describe to us today. And Rui is actually going to be joining the Simons Institute as a postdoc starting this fall. So really looking forward to hearing your talk. Please, can you share your screen?
Okay. Can you see my slide?
Yes.
Okay. Great. Okay. Thank you so much, Umesh, for the introduction and for giving me this opportunity to talk. And thanks everyone for coming. Today, I will be talking about a general paradigm, which is useful for optimizing fault tolerance schemes. We call this the flag paradigm. So first, let us recall the intuition for fault tolerance. So in general, in order to perform a quantum computation fault tolerantly, you need to simulate your circuit by running a larger circuit, which is more robust to noise. Specifically, you need to replace each gate or circuit component with more reliable gadgets consisting of noisy components. The so-called flag gadgets is just a technique which allows you to construct these gadgets with a smaller qubit overhead. And this flag technique is actually a general paradigm which has many applications. At below is a list of works that use the flag idea to achieve fault tolerance in a variety of tasks, such as error correction or magic state preparation. The key idea behind the flag paradigm is to use the so-called flag gadgets to catch those malignant faults in a circuit and then remedy them. In this talk, I will explain some of the details in these 3 papers that I have been involved with. All these 3 papers are joint works with my PhD advisor, Ben Reichart, in the past few years when I was at USC. The first 2 papers propose the flag idea, and they were written like 4 years ago. The third paper is a more recent result. In this talk, I will be mainly explaining how to do fault-tolerant error correction using flags. And I will only briefly mention other flag applications by other researchers. So now, let me first give some background and motivation for the flag. As we have seen for several times, fault tolerance is amazing because it makes it possible to perform large-scale quantum computations. For example, suppose you want to factor a 2000-bit RSA integer, or to simulate FIMOCO, which is an important molecule for biological nitrogen fixation. Then you're gonna need at least tens of billions of quantum gates. Thanks to the accuracy threshold theorem, you don't need to drive the gate error rate down to 1 of 10 million. And for small quantum chips, which is state of art, either based on trapped ions or superconductors, the average infidelity of 2-qubit gates is typically 1%, which is fairly close to the best fault tolerance threshold. However, it seems that the biggest obstacle towards fault tolerance is not the poor gate fidelity, but rather the huge overhead, which is defined as the ratio of number of physical qubits over the number of logical qubits. Even if the gate error rate is below 1 of 1,000, say, we still need several thousands of physical qubits to encode a single logical one. So a natural question is how can we reduce the overhead incurred by fault tolerance? This is a quite broad research field, and there are hundreds of papers on this topic. Most of this work focus on specific building blocks of fault tolerance schemes, such as synchrony extraction, decoding algorithm, or state distillation. Most of this work focus on specific building blocks. And each building block is already fairly complicated to optimize, and it's even more complicated to study the trade-off when you combine them. And among these methods, I want to in particular mention a low-hanging fruit, which is to choose efficient codes to work with at the very beginning. For example, we can simply encode multiple logical qubits into a single code block, such as the LDPC codes. This gives a higher rate because it can protect several qubits by a single round of error correction. For certain family of LDPC codes, we can actually achieve constant overhead, although this is mostly a theoretical result. The drawback for this idea is that it's difficult to target on individual logical qubits in a code block and compute over them. So for now, I don't think people have many good approaches to handle this issue. Previously, a kind of general approach for doing this is based on teleportation. So first, we teleport the several logical qubits to their individual empty code blocks. And then it will be easier to interact over here. And after that, we have to teleport them back to the data block. This is sort of expensive because we need ancillas with the size of a code block, and we need extra ancillas to prepare them in certain logical states for tolerance. So it's really desirable to construct efficient fault-tolerant operations for general families of block codes or LDPC codes. But I want to emphasize that it's also desirable to optimize on a specific code. For example, one should try best to reduce the fault tolerance overhead of a small code so that experimentalists can play with it on a small quantum device, for example, with tens of physical qubits. It might come as a surprise that although fault tolerance is at the heart of quantum computer, it has hardly been tested in experiments. People actually have demonstrated error correction protocols over several physical platforms, but they were not fault tolerant in the sense that a single gate failure in the whole procedure can occur in a certain way that propagates and become an uncorrectable error. And in the past few years, there have been several fault tolerance experiments on ion traps or superconducting qubits. Most of them are based on this 4-qubit error detecting codes with distance 2. And they use one or more ancillas to achieve fault tolerance. And recently, the joint group from Maryland and Duke, they demonstrate fault tolerance using this 9-qubit Bacon short code, which can correct any single qubit error. And this is quite a big achievement because they demonstrate they have tested logical state preparation, measurement, syndrome extraction, logic states, and even prepare magic states. And for all these tasks, they verify that the fault-tolerant circuits perform better than the non-fault-tolerant version. However, I would say the fault tolerance they demonstrate still have certain limitation. For example, the logical error rate of the single qubit gate is somehow worse than a physical error rate. This is just because for trapped ions, the single qubit gate is much better than two qubit gate. So since logical single qubit gate involves two qubit gate, then it somehow has worse error rate. Also, in their experiments, they were not able to perform intermediate measurements, meaning all qubits are measured simultaneously at the end. But in the long run, we definitely need to be able to perform error correction repeatedly. So testing fault tolerance, I think, is a daunting task. And I think the reason it's twofold. First, it's difficult to engineer reliable qubits with high fidelity 2-qubit gates and low spam error rate. And the second reason is that the criteria for fault tolerance is quite stringent and tricky to verify. And for this, I really want to refer you to this paper by Daniel Gottesman, where he gives a fairly extensive discussion about various caveats and complications. I don't have time to explain this idea in detail, but my point is that given such difficulties, what we can do is really to start from small devices. This is quite beneficial and also necessary to study because good tests will allow us to demonstrate the fault tolerance theory and will help us better evaluate the performance of different fault tolerance schemes in practice. And this in turn will enable us to adapt our schemes to realistic noise models. Therefore, I think it's important for theorists to come up with good fault tolerance tests to for experimentalists. And this is basically, the motivation and background behind the flag idea. Okay, so here are some small fault tolerance schemes using the flag idea. So first, for certain distance 3 stabilizer codes, only 2 extra qubits are sufficient for fault-tolerant error correction. The simplest example is a 5-qubit perfect code. We show that 7 physical qubits are enough to protect the single logical qubits fault-tolerantly. A more efficient example is the 15-qubit Hamming code. We show that 2 ancillars are enough to protect as many as 7 logical qubits. So now at this time, you may wonder why people have not implemented these small codes. People have already had chips with 20 or even 50 qubits. Well, the reason is that here I only tell you the number of physical qubits you need, but I don't tell you how you should interact them. In these flag schemes, we require a single qubit to be able to talk to every other qubit. And this condition is quite challenging to fulfill for many physical systems, such as superconducting qubits. Although such connectivity issue seems not exist for ion traps, these flag schemes also require reusing ancillary qubits by repeatedly measure and prepare. And as far as I know, there might be very few ion trap groups who are able to do such intermediate measurements, but their performance is quite unstable. So in other words, flag schemes do have certain requirements for the hardware, which need to be satisfied simultaneously. but I do believe it will be very soon that experimentalists should tackle all these issues. Okay, besides this error correction, one thing much more interesting we can do is to perform logical computation. We show that with only these two ancillars, you can already perform any logical gates within the 7-qubit Clifford group fault-tolerantly. And with another 2 qubits, you can actually perform any universal gate side on this 7 logical qubits. And previously, if we want to compute over 7 logical qubits, a reasonable plan is to prepare 7 blocks of Steen's code and compute over them. And you need at least 4 additional ancillars for example, to error correct fault tolerantly. So at least 53 physical qubits are necessary. And now we show that to achieve this task, you only need 19 physical qubits in total. The third result is an error correction scheme that is applicable to arbitrary stabilizer code. These small examples, they are able to achieve fault tolerance with very few qubits, mainly because they only need to tolerate a single circuit fault. But for higher distance, you probably need many more circuits for fault tolerance. But here we show that if the code has distance d, then you need at most d+1 ancillars in total. I should emphasize that this d+1 is a uniform upper bound for arbitrary d, arbitrary codes, which might not be tight for specific values. For example, when d equals to 3, and for specific codes, you need only 2 ancillars. So the main idea behind all these protocols are the same. That is to add gadgets, which we call flags, to those circuit locations where certain bad errors could happen. And if such error does happen, then the flag gadget should signal us alert. And provided our flag gadgets have been carefully designed, we should be able to correct the errors. Next, I will explain how to error correct using distance 3 code using only 2 ancillars. But before that, let's review some basics about stabilizer code error correction. In typical quantum error correction, the errors that we are concerned about are bit flip error X and phase flip error Z. In particular, X and Z are related by a conjugation of Hadamard matrix. To protect against a bit flip error, for example, we can encode a arbitrary qubit state alpha cat 0 plus beta cat 1 into this alpha 000 plus beta 111. Similar to the classical repetition code, no matter what alpha and beta is, the parity of any pair of the bits is even. Or in the language of quantum mechanics, the eigenvalue of Z1, Z2, and Z2, Z3 is always 1. And these polycheck operators are also called stabilizers. Suppose there's a X error on the second qubit. Then it will change the parity of the first 2 bits, or change the stabilizer eigenvalues to -1. So we can correct a single X error by measuring these parity checks and extract its syndromes. Similarly, we can protect against a phase flip error by encoding our qubit into a repetition code in the Hadamard basis. In this case, the code word is stabilized by X1, X2, and X2, X3. And a single Z error will flip the syndrome bits of at least one stabilizer. Now let's see how we can measure the syndrome bits without destroying the code state. For example, here is a circuit that measures Z1, Z2. So you first prepare the ancillary qubits in Cat0 state and perform two CNOTs controlled on the first two qubits. If there's no bit flip on the code word, then either the ancillary state is not flipped or is flipped twice. So no matter what alpha and beta is, at the end this ancillary will still be Cat0. However, if the second qubit undergoes a bit flip error, then the ancillary will be flipped exactly once. And at the end, you get a non-trivial syndrome bit by measuring the ancillary in the Z basis. Another way to verify the behavior of this circuit is by checking how Pauli errors propagate through this C0 gates. And in fact, in some sense, fault tolerance in general is all about how errors propagate through this multi-qubit gates. So for C0 gates, we can see that X on the control wire will propagate to the target, whereas the Z error on the target wire will propagate onto the control. So and the other case, the error does not spread. Now let's see what happens if there's an X error on the second qubit. So it will propagate through the C0 into an X error on the ancillary, which will flip Cat0 into Cat1 and result in a non-trivial measurement outcome. Similarly, we can verify that the circuit on the right is a valid syndrome extraction for X1, X2. So it's essentially the same as the left circuit, except changing everything from the standard basis into the Hadamard basis. So now let's see how the repetition. I have shown that this repetition code can correct a single X or a single Z error. But in general, we can construct stabilizer codes that correct many X, Z, or even Y errors. And here we use the notion of NKD to denote n-qubit stabilizer code with K encoded qubits, which can correct any Pauli errors with weight at most half of D-1. For the illustration purpose and also without loss of generality, in this talk, we only focus on how to measure X-type stabilizer and denotes the weights as W. Now let's take a closer look at the circuit that measures a stabilizer, for example, X tensor to the 4, and see how errors propagate within it. As we have seen, X-type stabilizer can detect Z errors. Suppose a Z error occurs here, then it will propagate through the C0 onto our ancillary and result into a non-trivial measurement here, as expected. However, in practice, errors not only occur on the data block, the syndrome extraction circuit itself is faulty. For example, there could be an X fault in the middle of the ancillary wire, and it will propagate through the subsequent CNOs into data qubits, and eventually this single circuit fault will result in 2 correlated errors on the data. If the underlying code can only correct 1 error, namely has distance 3, then in this case, a single X fault on the ancillary will give rise to data errors of weight 2, which in general is uncorrectable for distance 3 code. And in this case, in this sense, we say this circuit is not fault tolerant. More generally, if you are using code with distance D, then we say a circuit is fault tolerant if at the end of the circuit, the state in the code block remains correctable, as long as there are no more than half of D-1 circuit faults that have occurred. Of course, this is a very informal definition, but the key idea of fault tolerance is to keep the error propagation always under control. Okay, bearing this notion in mind, let's look at the Shor's method for fault tolerance syndrome extraction, which is one of the most popular methods people are using. Below is a non-fault tolerant circuit which measures X tensor 4. Its issue is that all the 4 data qubits are coupled to a single ancilla. So X fault in the middle will spread into high weight correlated error. One way to get around this is to have 4 ancillas and couple each data qubit separately with an individual ancilla. And this type of coupling is what we call transversal. So in this transversal signal, a single X fault can never propagate into correlated errors. Note that, so here, rather than a plus state, here the ancilla should first be prepared in this 4-qubit cat state, namely cat 0, 0, 0, 0 plus 1, 1, 1, 1. And at the end, the syndrome bit is evaluated as the parity of the sum of these 4 X basis measurements. Now, the issue remains that how can we prepare such cat state? So here is a simple circuit that prepares it in the blue shade. However, it suffers from the same issue that you have many C0 controlled on the same qubit. For instance, an X fault in the middle can propagate into correlated X errors on the ancilla. And then it will propagate further to damage the data block. So this circuit still is not fault tolerant. One solution for this is to use additional ancilla. Here is a blue color to check if there are any correlated errors on the cat state before interacting with the data. Note that we don't have to worry about Z errors on the ancilla because only X errors can propagate to the data. And it turns out that these errors on the first and the fourth ancillas are the only possible correlated errors arising from a single fault. And we can detect them by measuring the parity of the first and the second ancillas. Recall that the cat state is simply a repetition code stabilized by Z1 and Z2. So here we are measuring Z1, Z2. So the parity of the first 2 qubits is changed from even to odd. In other words, this X fault will propagate onto this verification ancilla and result in non-trivial measurement. So generally, in Shor's method, you start by preparing a large cat state and then measure the Z-type check operators to verify there's no correlated errors. And then you perform this transversal C0 only conditional on this measurement being trivial. So this is fault tolerant syndrome extraction circuit, which uses at least W+1 ancillas, where W is the weight of the measured stabilizer. Okay, now we are ready to talk about flag method. So this is a naive approach to measure, say, X to the tensor of 4 with spare ancilla. It's not fault tolerant because a poly X fault in the middle of the C0 can propagate to the data into correlated X errors. And previous approaches like Shor's method get around this issue by making the C0 coupling transversal. But in flag paradigm, we allow this to happen. The point is that we are able to cache it and correct them. So this is the flag gadgets colored in blue. So the flag ancilla is initialized in state cat0 and coupled to the syndrome ancilla with 2 C0s, and then finally measured in the poly-Z basis. If there's no fault, then the gadget does nothing. So you get your syndrome bit here, and the Z measurement on the flag is trivial. And if an X fault happens, it will still propagate badly to the data. But in the meantime, it also triggers the flag measurement to be non-trivial. So basically, the key for the flag gadgets is to catch all possible X faults in between them. And this is the whole point of a gadget, and that is actually the main idea of the flag paradigm. But the tricky thing is that there are other scenarios where the flag could be triggered. For example, the flag ancilla itself could fail, and you can get a measurement, non-trivial measurements, but there's no data error at all. Also, X fault here will generate weight 3 data errors, but it's equivalent to X on the first data qubit modulo the stabilizer. And similarly, X fault here will generate a weight 1 error. And this XX error is really the only correlated error that we have to correct. But the only thing we have observed is this triggered flag. So how can we distinguish between these correlated errors with these weight 1 errors? Well, the solution is that we can measure the stabilizers to extract the syndromes of this unknown flagged error. We should be able to distinguish these flagged errors if they give rise to different syndromes. But to do this, you have to carefully design your flag gadgets. And in particular, the order of the C0s within the flag is really important. So now let me illustrate this idea with an example. Suppose we are using the 15-qubit Hamming code and want to measure one of its stabilizer X tensor 8, which is supported on the first 8 physical qubits. So here's a flag circuit that measures it. I don't show all the 15 qubits because we are only using the first 8 of them. So here we arrange all the C0 gates in this trivial order. And this flag gadget is supposed to catch X fault occurring in the middle. Now let's look at this specific X fault in the middle of ancilla where it will propagate through subsequent C0 gates all the way down to the data qubits. And in this process, it's also trigger the flag measurement to be non-trivial. And finally, it will result in X errors on data qubits 5, 6, 7, 8. And you can verify that this operator is not a stabilizer, but it has trivial syndrome. So in other words, it commutes with all stabilizers and is a non-trivial logical operator. So in this case, we should definitely correct this unwanted logical error. However, in another scenario where the flag can be triggered simply by a measurement fault on itself, so there's no data error at all. And in this case, we should do nothing. But there's no way that we can distinguish this scenario from this weight 4 logical error. So this circuit is not fault tolerant because a single circuit fault gives rise to a logical error we cannot detect. So how do we solve this issue? Well, it turns out that we can simply change the order of these C0s. For example, we can switch these 2 C0s and switch these 2 C0s. Still, X in the middle will propagate into a weight 4 correlated error on the data. However, the resulting data errors in this case have a non-trivial syndrome. So this circuit is better than the trivial order C0, but it's not done yet. Here I label all the circuit locations where a single fault could trigger this flag. Unfortunately, if you write down all the possible flag errors, you can verify that they all have distinct syndromes. So this circuit is fault tolerant in the sense that they are able to diagnose the potential correlated errors by its syndrome and apply the correction accordingly. And so far, we have considered only error correcting distance 3 code, where we only worry about at most one circuit fault.
Sorry, can I ask a question?
Sure.
Sorry, so you did something that I got a little confused on the previous slide. Somehow you switched the order and I didn't understand exactly what was going there. Could you say that one more time?
Yeah. For example, if you look at this circuit with a non-trivial order of C0, then this fault will propagate into a correlated error with non-trivial syndrome. And the specific correlated error actually depends on this, the order here. Right, so you can compare this slide with like this case. If you change this to or this to, then this X fault will not propagate to qubit 5. Instead, it will propagate on qubit 4.
So could you change the order at random and it will work, or is there some specific rule by which you change the order of C0s?
Yeah, I mean, you can easily, I mean, given the C0 order, you can easily write down the resulting propagated error, but you have to manually, you have to calculate its syndrome. When the error rate is high, then you definitely want it to have a non-trivial syndrome, and that will depend on the property of the code. So, yeah. So yeah, that brings to next question. That actually so far we have only considered distance 3, where we worry about single circuit faults, and for general distance 3 code, it is a priori unknown if there exists any flag circuits using only 2 ancillars. This is the reason is that for any specific code, we need to find a C0 scheduling so that the flag errors arising from a single circuit fault are distinguishable. So a natural question is how to design flag circuits that fault tolerantly error correct high distance codes. It seems quite difficult problem because we need to deal with a combination of multiple circuit faults. The intuition for how to tackle this is to protect the syndrome ancilla with more than one flag gadget. And in this way, the flag measurements will give you more bits of information, and that will allow you to better locate the critical faults on the syndrome ancilla. The guiding principle for this is that we have to make sure the bad faults are always flagged, and all possible flagged errors can be distinguished by either the flag pattern or their syndromes, or combined together. In the recent work, we use this intuition and provide a flag error correction scheme that works for arbitrary stabilizer code. And our scheme still measures one stabilizer at a time. And for distance D code, it uses the flag circuit use at most this many, at most D+1 ancillars. And in particular, our circuit construction does not, it's a explicit, and the order of the C nodes does not matter. Namely, any C node order would be fault tolerant. Okay, so much for the error correction. Now let's consider how to do fault tolerant logical computation with flags. First, let's recall how to perform universal computation without using error correcting code. So universal gate size can be generated by Clifford operations supplemented by any additional non-Clifford operation. So here, Clifford operation includes preparation K0 states and Clifford group unitaries generated by these gates, and also a measurement in the Z basis. And the limitation of Clifford operation is that any computation using only Clifford operations can be efficiently simulated on classical computer using the so-called polyframe updates. And in fact, using these rules, all Clifford unitaries can be moved to the end of the circuit and absorbed by the final measurements. So in principle, you can achieve all the Clifford operations by only preparing K0 and measuring arbitrary poly operators. And to achieve universality, you need one non-Clifford operation. One example is to use certain resource states called magic states, such as T state and H state. Alternatively, you can directly apply a unitary outside the Clifford group, such as T gates and the control Z gate or CCZ gate. So in summary, for fault tolerant computation, you need to perform the logical versions of Clifford or non-Clifford operations over the logical qubits encoded in the code. So here are some examples where we can use flag gadgets to make these logical operations fault tolerant. For example, in this paper by Hansumanon et al., they provided flag circuits to fault tolerantly measure the logical poly operators of cyclic CSS code. And as we have seen, these measurements are sufficient to implement any Clifford operations. And in these two papers by Chamberlain et al., they prepared the magic H states using the seven qubit stain code and the color code respectively. They do this by fault tolerantly measure the logical Hadamard operator using flag circuits. And finally, in the paper with Ben Reichardt, we consider the 15 qubit Hamming code, and we construct logical CZ and CCZ gates using physical CZ and CCZ gates. And to make them fault tolerant, we replace each physical gate with a corresponding gadget. Another application of flag that I want to mention is this recent paper by Drifto De Broglie and Ken Brown, where they extended the flag idea and construct more general flag gadgets, which can be used for magic state distillation and arbitrary angle poly rotations, which is a useful circuit for simulation of quantum chemistry. And their flag gadgets serve as error mitigation by catching a subset of errors within the flag. Finally, let me try to give some broad perspective about flag fault tolerance in general. So flag technique is useful for designing small flag, small error correction or detection schemes, which are useful for near-term fault tolerance tests. But it's also interesting to look at large infinity code families and to devise flag schemes for them. For example, here are all the the partial list of examples where, for example, Chamberlain et al., they look at they apply the flag technique to the topological codes such as color codes and devise efficient decoders which take advantage of this flag measurement results to achieve better decoding performance. And I want to conclude my talk with a very broad open question of device flag protocol by taking into various by taking into account these factors like the number of ancillary qubits or the number of parity checks measurements required, or if you are considering parallelism, you may care about the circuit depth, or for the superconducting qubits platforms, you may have limited qubit connectivity or degree. And also a major drawback of our flag flag scheme is that it uses a lot of intermediate measurements. So if your measurement time is long and say the idling qubit error is not negligible, then you certainly want to use as many measurements as possible. So and also it's interesting to develop flag schemes specific for hardware noise, such as biased or biased noise for like superconductors or quantum dots, or for anisotropic errors for trapped ions. And I think this so that depends on which one of this is your priority, and how you measure the trade-off between them. And I think this is also a broad question for not only for flag, but also for fault tolerance in general. So with that, thank you very much for attention.
Wow, thank you, Roy. That was a fantastic talk, really clear. Let me turn to our moderators to see if there's any questions.
Yeah.
IQ, you have a question?
Yes. Hi, folks. Rui, I really enjoyed your talk, and it occurred to me while you were describing the flag protocol that in many ways you could consider it a classical protocol, where the insight is that the error detection or error correction protocol can introduce more errors as long as you find a way to uniquely identify them and disambiguate them. And so at least in the examples you gave, it's a purely classical protocol. Are there examples of flag protocols which are non-classical?
I would say, in that sense, I agree with you that currently, at least for error correction, the flag schemes is really a purely classical problem. But for example, if you want to, if you look at the flag gadget for physical CCG gates, which is a non-Clifford gate, then you have to consider a linear combinations of Pauli operators, which can be regarded as something quantum, but still, it deal with Pauli operators. You can also say it's a classical problem.
Sorry, may I ask? I mean, in quantum error correction, you always correct in the X and Z basis. So would you say all of error correction is just classical? Quantum error correction is just classical? Is that the sense in which you meant it, or can I ask you to refine what you were saying, Ike? I didn't quite understand.
Absolutely. Go ahead, Roy.
Yeah. So here I only consider marrying Pauli X type operators, but this is just for illustration purpose. But for general scheme or general code, you can definitely measure arbitrary stabilizer you want, which is a mixed type. And yeah, but yeah, but the key is that you have to choose which stabilizer to measure carefully or cleverly, so that the resulting flag error are distinguishable somehow. Yeah.
Thank you. Maybe I'll respond to Umesh and then hand it back to you, Rui, to amplify more. I wanted to try to understand this from a more general perspective as an idea which could be used for non-stabilizer codes. Because as you point out, of course, if it's in a CSS framework, then you just do X and Z separately, and it's just like two classical codes. But if we think of flags as being the concept that the error correction procedure or whatever procedure that's fault tolerant can introduce new errors as long as you can still disambiguate them, then maybe it opens the door to being used that way for other kinds of codes.
Yeah.
Like maybe you could use that principle to build fault tolerance into CWS codes, etc.
Yeah. I know CWS code, but I don't know if there's any explicit protocol for doing computation.
No, not that I know of, and so maybe this could lead to something like that.
Yeah. So I guess the flag idea can definitely be applied to non-stabilizer code. If I think people like Timberland et al. They consider using flag to error detect the GKP code, which is non-stabilizer code. As I think that's a interesting question. So first you have to come up with a fault tolerance criteria for your physical system, and then you should come up with specific circuits that realize that your logical operation, and then you can devise flag gadgets to catch the critical faults that could have occurred. Yeah.
Thank you.
Thanks.
Great, thanks.
So,
thanks.
I have a question kind of on a related note. Is there kind of a general paradigm for choosing this C0 measurement order or something? Like, it seemed like you had to very carefully figure out the C0 measurement order so as to disambiguate the different places the error could have occurred. Is there like a general way of doing it, or you have to custom do it for each kind of stabilizer code you're looking at?
Yeah. So I think the goal we want to achieve is to distinguish the flag errors, and there are two ways to achieve this. So first, we can use more flag gadgets, using more flag qubits, so that the more flag gadgets will give you more information about different error could generate different flag patterns. So the second way is that you can extract the syndrome of the unknown errors, but the syndrome will highly depend on the code structure itself. So I think for general code, it's very difficult to have a framework for finding the C0 order. But for certain code with certain structure, for example, for Hamming code, we have shown that for all Hamming codes, we give a explicit C0 ordering, which can give you distinct syndromes for the flagged error using only 2 ancillars.
Got it. Thanks. Yeah, so it sounds like something that really has to be done custom for each code based on the particular structure.
Yeah,
Thanks.
exactly.
So there's a question from Harvey Hu. Are the 2 types of errors you mentioned all that's possible in a quantum system?
Sorry. So what are the two other errors?
Probably X and Z errors. That's what Harvey means. I'm not sure. I mean, maybe Harvey can clarify. Oh yeah, maybe there's a yes. Okay. So the question is yes. The answer is to the question is yes. Yeah. Are X and Z the only two types of errors that are possible?
Okay. Are there any other questions for Rui? Okay, so maybe yeah, it's almost time for the panel. So let me just thank you, Rui, again. That was a fantastic talk. And okay, so let me just let's move on to the panel now. So I want to you know, at this point I should be saying, well, you know, I'd like our distinguished panel to step up to the front of the stage, but you know, what I think what that means in our case is that the Zoom experts here are going to pin the videos of everybody on the panel. So, you know, I just want to see John Martinez and John Presco and Peter Shaw are here, as well as our two speakers from today and last week, Rui and Daniel Gottesman. So.
All right, I'm going to start pinning the panelists right now, so just a second.
Mm-hmm. So, so while that is being done, let me introduce our very distinguished panel. So we are really lucky to have three of the giants in our field: John Martinez, John Presco, and Peter Shaw. John Martinez, you all know about. You know, he's an experimentalist who worked on superconducting qubits, and he was the architect of Google's quantum supremacy experiment. John Presco, you know, we go back a long way. He's one of the earliest physicists to take quantum computing seriously. He's worked on, you know, all aspects of the subject, including error correction and fault tolerance, and in many ways, he's shaped the quantum world we work in today, you know, including NISQ and even the notion of quantum supremacy. And then Peter Shaw, you know, he needs no introduction. He certainly revolutionized quantum algorithms with his quantum algorithms for factoring and discrete log. But he's also the inventor of quantum error correction and fault tolerance. So, you know, I really cannot think of three better people to be on this panel, you know, to talk to, you know, to talk about these, discuss the two talks we had already. So, you know, in terms of the panel, you know, the plan is to have each of the three panelists, you know, give a 2 to 3 minute sort of talk discussing their views about these talks, but also more generally about you know, quantum error correction and fault tolerance. And then we'll have a more general discussion for a little while between the panelists and the speakers, and then move on to questions from the audience. So you know, before we start with the individual views, you know, I spoke to a few of my colleagues about what they would really like to hear about, given this unique opportunity. And so let me put out a few ideas, you know, which you can feel free to incorporate or not, as you like, in your remarks. So they range from questions such as, could you say something about, you know, how essential do you view fault tolerance to getting to anything useful in quantum computing? You know, is it an essential first step, or do you think we can get somewhere first? To questions like, can you describe any experiments that would, in the near term or in the medium term, that would probe some critical concepts in in fault tolerance? You know, are there specific experiments that you'd like to see or can point to? You know, all the way from there to questions about in our current fault tolerance models for the theoretical results, we assume independent errors. And so, you know, do you think it's time to move towards fault tolerance in models where there are correlated errors, where, you know, for instance, with superconducting qubits, with crosstalk, or how important is that aspect? And then, you know, then there's of course questions about continuous quantum error correction. You know, is that something we should be thinking about? So with that, let me just turn the floor over to the panel and see if you know, who would like to go first? Maybe alphabetically, John Martinez. Do you think?
Okay.
Well, welcome to this panel.
Great. Can you hear me okay?
Yes.
Okay, great.
Yes.
Yeah, thank you very much for the invitation. There were several, I had something to say, but I was going to say something about maybe a question or two of yours. In terms of doing experiments, one of the things that I worried about was, can we really, as we build a big system, can we really understand what the error rates are and what the errors are? And, you know, you can maybe measure your 1 and 2 qubit errors, but then when you run a big code, are you going to get that? And that's in fact the main reason for me doing the quantum supremacy experiment, was to run a complex algorithm and check to see whether the error rates made sense. And in fact, that was probably the most astounding thing that we discovered in running that, is that you could predict the net error rate as measured by cross-entropy fidelity, the system error rate, which, you know, cross-entropy measures what's the probability that there were no errors in your whole sequence running the quantum algorithm, and you could check that versus your known single and 2 qubit errors, and it was quite good. I was actually quite surprised that it was quite predictive of it. And what this means, and you can check various issues with that, but you can basically check that the basic physics is working right, kind of thinking about an error correction model. And to me, this is really great. Now, when you run an error correction, you also have to worry about correlated errors. And the cross-entropy benchmarking experiment, if you have 2 errors, whenever, you know, you had 1 error, you also had a second error, you couldn't measure that, okay? So you don't really measure correlated errors, you just measure if there's 1 or more errors. So that still has to be checked. And that's, of course, very important for quantum error correction. But I think that's, you know, super important that that's looking good. And I expect that. There's another question, you know, can we look for correlated errors? There's a paper coming out by the Google group on correlated errors, I think in next week or so in Nature Communications, and there's an archive paper on it right now that you can look up that looks at leakage to, let's say, the 2-state and superconducting qubits. And it does an experiment to measure that leakage and then do some qubit reset to correct for that. So there is some experimental work on that. And, you know, we were happy that, you know, referees saw the importance of that and accepted the paper and, of course, fixed it up, improved it some. So that's going to be out there. I think that's really good and be useful for people to start seeing data about that. And the last thing I wanted to share, sorry if I'm taking too much time, but I like very much this last slide by the speaker where it talked about, excuse me, I'm trying to share here, talked about specifications a little bit. And the thing is when you build an error-corrected system, it's a systems problem. There are many, many things to think about and get right. Okay, and there was a nice list there. Here's a longer list. It's probably longer than this, but these are the things I think about. And you have to get many things right. So it's good people are thinking about new codes, trying to fix things up. But remember, you have to do 10, maybe 20 things right in order to make it useful for experiment. Just going down the list, you need a good threshold. What's the qubit number for an exponentially small error? What's the architecture, specifically the connectivity? More connectivity, the harder it is to build. Error decoding complexity. Can you actually do it on, let's say, a supercomputer even? How to do one logical gate, how to do CNOTs, how to do measurement. Can you do your logical gates in parallel? Because that's how computers work. You want to make it fast. Can you do long distance logical gates, T-state distillation overhead? And then finally, you're sensitive to correlated errors. And I have a paper that came out recently talking about cosmic rays. And cosmic rays, at least for solid state qubits, give you correlated errors. And you have to think about what's going to happen there. In fact, having more qubits is a little bit better in that case. You don't want too many, but that's okay. And I give an example of the surface code. And basically, the surface code meets all those things in a way that's reasonable. You can imagine building something. Of course, we don't want to make it better, and that's great. But make sure you understand all those issues, I think, is the main thing that I want to say as people explore error correction codes, different ones. What are all the system things you have to worry about? And are you trading off something good for something like really, really bad in terms of doing experiment? Because basically, if you have one of these things that don't work well, then you're not going to use it experimentally, at least, to get to a big quantum computer. Okay, thank you. Thank you for letting me share.
Thanks, John. I guess John Prescott.
All right, well, first of all, I want to just take a moment to celebrate what a marvelous idea quantum error correction is. Some of the people on the panel, like Peter and Dave and Daniel, and some of the people in the audience remember in the mid-90s how much skepticism there was from good scientists about whether quantum computing would ever be scalable. And they had reasonable basis for that skepticism. Physicists, both experimentalists and theorists, understood in particular how pervasive decoherence is, and that we can, at least theoretically, envision scaling up quantum systems to arbitrarily large ones that we can control. We can make them do what we want them to do. This is an amazing and great thing. And it has very broad implications in physics. It's giving us new insights into phases of quantum matter and even quantum gravity. So I think this is one of the best examples we have of how the lens of computer science and information theory blended with physics allows us to advance physics. It's really hard to do. What should the goal be? You asked, how essential is fault tolerance? It's essential for the long-term future of the field. What's the goal? Well, we'd like to be able, using fault tolerance, to execute algorithms which will be of practical interest that we wouldn't be able to reach without using error correction. It's possible we'll be able to do interesting things with NIST devices without error correction, but there's no guarantee of that. So it certainly has to continue to be a focus of our field to proceed to advance along that path towards really scalable quantum computing. And underlying the two excellent talks by Daniel and Rui was what makes it extremely hard in particular is the high qubit overhead. And they each in their own way were talking about how to mitigate that. Daniel in a sort of more futuristic way, talking about these higher rate LDPC codes. Well, it's important to think about the future when we'll be able to do those things, which might require lower qubit gate error rates and higher connectivity than with the current generation of devices, but eventually we'll be able to do those things. And that's an important frontier for theory. And Rui talking about the clever use of ancillas through the flag paradigm to reduce the cost. And those are both important things. You asked about what experiments we want to do. Well, following up on what John said, we need to benchmark error correcting codes at the logical level. We need to see how well we can execute logical circuits, not necessarily ones of practical interest in the near term. This recent Google experiment that John mentioned takes a good step in that direction. Now they're just doing the repetition code. It's not really a quantum error correcting code. They can correct either the X errors or the Z errors, but not both simultaneously. But what they were able to do is multiple rounds of syndrome measurement, up to 50 rounds. And they were also able to study how, as you increase the length of the code, the logical error rate goes down, more or less in accord with expectations based on their understanding of the noise in their device. Now there was crosstalk and they could see it, but error correction still worked pretty well. What I'd really like to see, of course, is lower 2-qubit entangling gate error rates. That's really a challenge that, error rates in both the superconducting circuits and the ion traps are a bit below 1%, not quite good enough. Give me 10 to the minus 3, 10 to the minus 4, and then we're starting to get somewhere. And I realize how hard that is, but it's really an important goal. And so people should be, trying hard, of course they are, to improve those gate error rates, because that'll have a big impact on the overhead cost of error correction, and also it'll enable us to do more in the NIST era. And it's important to continue running these things on multiple platforms because they have trade-offs, pros and cons, and we don't know at this stage what's going in the long term to have the best prospects for scaling. So that continues to be important. Maybe I guess I'd like to say a little more, but I'll stop for now about how we might be able to improve gate error rates and get into an interesting regime with quantum error correction sooner. But that's
great. That's a fantastic perspective. We should definitely get back to what to discuss these things. So Peter.
Yes. So I want to say that these last two talks about flag qubits and LDPC codes are really, great advances in the theory of quantum error correction. And you can ask, are there going to be a lot more advances in quantum error correction and quantum fault tolerance? And I think there are. In fact, if you look back at the theory of classical error correction, Shannon came out in 1948 with his bound on how good you could possibly do in terms of classical error correcting codes. And for the next 40 years or so, people, improved them, but they never got close to Shannon's bound. And then around 45 years after Shannon's paper, these three French engineers were, basically trying to improve the performance of convolutional codes and had a clever idea. And they tried it out on their computer, and it came with a fraction of the Shannon bound. So they published it. And theoretical coding theorists didn't believe them. So then the theoretical coding theorists coded it up too, and it worked. And it took another 5-10 years before anybody, we still don't have a proof that the original scheme works, but we have a proof that LDCP classical codes, which are very similar to the original turbo codes, do work very well, but they don't quite make the Shannon bound. And then another 10 years later, someone else had a really clever idea, and he came out with polar codes, which provably met the Shannon bound. And at first, polar codes weren't practical at all, but then people started working on them, and they are now, I think, going to be used in the next generation of cell telephones. So, even 60 years after Shannon's original paper, people were improving the theory of classical error correcting codes. So I think that there's lots more you can do to improve the theory of fault-tolerant error correction. And if we do that, it will bring the actual implementation of fault-tolerant, real useful quantum computers a lot closer. I mean, we still are probably not going to be able to get good quantum error correction at 1% error rate. You probably need to go down to 0.1 or 0.01% error rate to get really good error correction. But I think, we don't need to just concentrate on the hardware. We also really need to concentrate on the theory and the software. And it's possible you can even get more, speed up from the software than from the hardware.
Oh, great. Yeah. Thanks, Peter. So let's see.
Just
Yes,
make a
John.
comment on the last two things. I really liked the discussion about how we have to improve the 2-qubit gate errors. As maybe people know, I've been harping on that for years. And it seems that you can build complex systems with about a 1% error rate for 2-qubit gate fairly readily. And then there are isolated examples where you're doing better than that. And we just need to continue at it. It's just hard for a variety of reasons to get there. But I do have optimism that if you work hard enough, we can bring down that number. But I'm going to say, given that it's been many, many years experimentally that people kind of have been at this level, it's going to be hard. And although I think you can get to 0.1%, maybe it's just going to be really, really hard to get lower than that. So I think, really efforts on not just reducing the qubit number, but also, tolerating high error rates, around 0.1%. What can you do with that would be interesting for people to understand. We all hope that we can do better than that, but there's a chance that it's going to be really, really hard to get much below that, and just be aware of that. That's a possibility for the future.
Great. So let's see. Let me just ask people in the audience to put in their questions in chat or in Q&A. But in the meantime, Daniel or Roy, do you have anything to add before we turn to the audience?
Not really. I mean, I just want to second some of the stuff that's been said. Obviously, in the vicinity of 1%, we can do error correction and fault tolerance, but there's limited choices and you're kind of right at the margin. You get down to 0.1 or 0.01%, and you have many more error correction options and much more room for additional errors from various things. I think crosstalk, something else that's been mentioned a few times, is a good future frontier in error correction and fault tolerance. It's something that hasn't really received enough theoretical study yet of how we deal with that fault tolerantly. I mean, I know of one paper by John Martinez and Austin Fowler that studied it, but there needs to be more, I think.
Great. Yeah, I see that Ike Chung has a question. Ike, do you want to?
Sure. This is a question for John Preskill, more or less an excuse to let him continue his thoughts. But John, another John von Neumann, many years ago, would have said about his computing infrastructure at the time, absolutely fault tolerance is necessary. We must study our vacuum tubes to understand their flaws intimately because they are the future and fault tolerance is absolutely required. And as you know, that didn't transpire. We have the silicon transistor instead. So what are your thoughts? Are you going to be obsolete in your thoughts in the same way, or is there no option other than what we have?
Well, I think actually I would like to believe that in the long run, we will have far, far better quantum hardware than we have now with much lower error rates. And, there is some vision of approaches that might at least move us in that direction, the best known being topological quantum computing, which is a brilliant idea. And people have been pursuing it aggressively in the lab for 15 years, and progress has been very slow. That doesn't mean it's not going to eventually break through. I think doing error correction at the hardware level, incorporating protection against noise into the design of the hardware is a really important approach. It will pan out probably in the long run, but it might be the very long run. We don't really know, of course, just like von Neumann couldn't anticipate very well the future of microchips. But I think chances are for quite a while, once we are able to do quantum error correction and perform quantum algorithms that are really impactful on society and people's lives, that will require quantum error correction until sometime, perhaps in the rather distant future, when the quantum hardware, by one means or another, becomes such high quality that error correction is less important. I think, you know, if you can do better by, even when, if physical gate error rates are much lower, if you can extend the reach by doing quantum error correction, if assuming the error rates are not completely negligible, then you'll want to do that.
So, sorry, John, can I just follow up, ask you a follow-up question, which is, you wouldn't say that there's something very, very different about quantum information that makes, you know, well, you could say that in classical error correction, it's really the repetition code that works for us in hardware. But with quantum error correction, are things so different that we wouldn't expect the same sort of outcome where things become completely stable just at the level of hardware, or would you, where would you come down on that?
Well, you know, for von Neumann's original arguments were based on the repetition code. There is, you know, a physics setting in which the repetition code is very natural, which, you know, is relevant to actual hardware, that magnetic systems, you know, in 2 or more dimensions have memory times which scale very favorably with the size of the system. You can think of that as a repetition code, but with highly redundant checks, which are, you know, provided by the dynamics of the system itself. That's kind of the vision of topological quantum computing as well, that the physical system should be intrinsically resistant to noise. It doesn't really work, even theoretically, as far as we know, in just 2 spatial dimensions, in the same sense that the repetition code can work in 2 or 3 spatial dimensions. But it's an open question, I guess, in 3 dimensions, whether we can make a stable quantum memory which can store quantum information for an indefinitely long period. I think that's also, for theorists, an important question, which could have a big impact on the future of the subject.
Great. Are there any other questions from the audience?
I think Daniel has to get something off his chest. He's got a really deep frown.
I was just looking, there are some questions I see in the Q&A.
I see.
One of them is, what is the status of topological qubits, which John started but didn't say too much about. Do you want to say more about it?
Oh, this is back to me?
Well, I think you're the best on the panel.
Well, the status is that the current approach, which dates back about 10 years to realizing a protected qubit using Majorana modes in a quantum wire, hasn't yet succeeded. And we still don't have a protected qubit. And, you know, good scientists have been working towards that. And, you know, eventually I think it's going to succeed. When it first succeeds, it won't be a perfect qubit. We won't have arbitrarily low gate error rates. We'll use error correction on top of it. The hope is that that approach will lead on a reasonable time scale to lower gate error rates than other hardware approaches. But evidently, it's very hard. Part of the challenge is materials issues. And this is a challenge actually for all the solid state approaches to quantum computing. And those things take time to solve.
Great. There's one other person who has a hand raised, Jan Lomart. Can you ask your question?
Thank you very
Are
much.
you muted?
Sorry, I'm just speaking. I meant very interested in the talks. Thank you very much so far. I'm wondering, there's a lot of interest in the ultimate goal of the Majorana qubits. At the same time, shouldn't we have a kind of approach in gradual improvements? And once we achieve the logical qubit level, then maybe it becomes easier to replace the underlying hardware. I mean, we want progress instead of waiting for the ultimate perfect qubit.
So I can comment on that, and I would say the approach that I was thinking on at Google was to do exactly that, to use the surface code as a prototype because it fit in with the superconductivity, and the quantum supremacy was a milestone along the way to make a 2D grid and do the surface code. So there's this latest paper that gave some information. Google's now working on a 2D version so that you can actually correct bit and phase errors simultaneously and repetitively. And so people are doing that. It's just hard. That's why it takes long, but that will proceed. And when I was thinking about that, I had a vision how to scale up to way more qubits so that it would be possible to do it at multi-order and understand the physics of this very well. Again, the big thing that has to get figured out is lowering the error rate so that the overhead is not so high. Again, to around 0.1%. But that was certainly my vision, and I think that Google's continuing on with that vision to try that out. And yeah, that might be the first steps to see what's going on. And then when people invent something better, either hardware or algorithm, you can take what you learned and do that. So I think that's on people's minds for their roadmap.
Great. I promised to circle back to John, John Fresco, because he had said he had these remarks he wanted to make that he didn't have time for. So,
well, but first of all, just to follow up on the last couple of comments, I mean, we shouldn't think of topological qubits as seeking the perfect qubit and leaving the software approach behind. And what John was describing, John Martinez, is certainly something that we've got to do to take whatever the best hardware we have that we can scale up to a reasonable number of qubits and see how well quantum error correction works. Topological quantum computing is an approach to trying to get lower gate error rates. Might not work, but it's important to pursue that and other ideas. The other idea I wanted to mention is the possibility of using, which the Yale group has been working on for years, and lately there's been, I think, a notable advance on the theory side from the Yale and Paris groups, is using the resonators in superconducting circuits as the depository of the qubits, and where the noise can be engineered so that it's highly biased. So, and one can, so that, but what I mean by that is, we have Z and X errors like Rui talked about in his talk, but where the Z errors are far more frequent than the X errors, we can concentrate most of the error correcting power on those frequent Z errors, less on the less frequent X errors, and that can lower the overhead costs of error correction substantially. And the recent development that came as a surprise to me is, of course, you want to be sure that your circuits don't propagate the noise that occurs frequently, which your code is designed to correct, to the less common errors which your code doesn't protect against as well. And formally, a C0 gate is good from that point of view because it propagates X errors to X errors and Z errors to Z errors, but we have to remember that it's actually a physical process, and so you have to worry about errors occurring during the execution of the gate. And it turns out that in the appropriate setting, which we don't really have time to go into, the C0 gate, even though noise is occurring during the execution of the gate, if it's done the right way, can preserve that noise bias. And so, of course, there are many challenges associated with this approach, but I think it's an important one to pursue and is promising because if it indeed turns out to be the case that we can scale up devices with highly biased noise, that could substantially reduce the overhead cost of doing error correction.
Dan has a question. Dan, do you want to ask it directly?
So I guess the question is about modularity. So I figured that, however big the next Google chip is, it's going to be a finite size chip. And then, true scaling is to grow to infinity. So you're going to have to eventually learn how to connect quantum computers to one another. Does that present specifically new challenges to error correction and fault tolerance?
Sure. I don't know, it's always me. Okay. Yes, of course it does. And it's particularly challenging for the ion trap approach, where there's a limit to how many ions you can put in a single trap and still maintain good gate fidelities. And there are two solutions to that people are pursuing. One is to move the ions around in a large system and then have small modules in which the processing occurs. And then you need the ability to move the ions around without losing coherence. And then you have to cool down their motion when they come to wherever you wanted to send them. And the other approach is to use photonic interconnects to connect traps together. And there are big challenges associated with both those things. It's important to pursue those technologies as well. And, those are problems that it's going to take time to solve.
Yeah, let me make a comment about superconducting qubits. When we were thinking about this, we thought that we could scale up to, say, 1,000, 10,000 qubits using just the regular silicon wafer, what we're doing right now. Which of course is big enough to do a lot of testing on getting low error rates and doing logical gates. And then to go beyond that, you would have to connect them together in some way. And there was some simple in conceptually ways to do that, but you would have to develop a lot of ideas to get that to work. So there is kind of a pathway forward on that. My view is you have to really get things working as you right now at 50 qubits, whatever, and then you have to get it working at 1,000 qubits. But there is a path forward there for superconductivity, we think.
John, since you went in that direction, can I ask you what your ambitions are moving forward? What are you actually going to be working on or trying to get to? What kind of hardware, etc.?
Yeah, well, unfortunately, because I had to leave Google, I can't work on the big systems that I would like to do. But I am working and I'm looking at opportunities right now. But the big thing I've been working on is fixing the error rates and making them smaller. So I wrote a paper on cosmic rays and correlated errors, and I think we know what to do there. That looks good. And I'm also writing some papers and working with Robert McDermott on how to improve the individual qubit errors. And I have an idea on how to make that. But mostly what I'm going to do is I'm just going to focus on that issue because, you know, that's the critical issues we have to do. And, you know, what I did for the last 3-4 years at Google is I was working on how to scale up, basically doing the wiring. It sounds really boring, but that's what you have to do to scale up. And I more or less know how to deal with that. So, you know, we're making progress. It just takes a long time to figure all this stuff out.
So I did want to say something about the kind of the approach to fault tolerance with modular systems. I think it's not fundamentally different or new. I mean, I think we have a lot of fault tolerance tools already that can handle that. It depends a lot on what kind of the parameters of the modularity are, right? If it's very small modules versus very big modules, that suggest totally different things. It depends what the error rates interconnecting different modules are compared to the error rates inside a module. And it depends on what the connectivities between different modules are. So, you know, you have to kind of look for your specific system, what those 3 things are. And then maybe that also requires some additional design work to figure out what the right fault tolerance architecture to use is for those parameters. But, and eventually, you know, once that's all worked out, maybe we'll want to come up with even better ones that are beyond the current tools. But the tools exist, I think, to deal with that.
Yeah, I was really talking about the hardware challenges more than that. I mean, we want to have much higher communication rates between modules, say, than they currently do with the ion traps.
Yeah, and in my particular idea with the superconducting system, it would be an interface between modules that would allow for fast and parallel communication, which again is the kind of thing you want to try to do. I agree though with the sentiment that having photonic interconnects so that you can have really separate out the modules is a great direction. But unless you have the communication speed and the you know, which is the number of bits too, or qubits that you're sharing, then that you know, that becomes a bottleneck. So this is pretty far out. You know, we have to get the basic modules to work well.
Great. Well, I think we are getting to the end of the panel. Let me remind everybody that we'll be on GatherTown at this point. So that should be, I think there'll be a link on the chat if you don't already know. So with that, let me thank both of our speakers for last week and this week for superb talks, and to our distinguished panel for, you know, really great discussion. So thank you, everybody, and see you at GatherTown.
Bye-bye.
You just make sure the GatherTown link is there. Okay, so you should be able to find the link to GatherTown in the chat.
Umesh, just a quick comment. Some of us use a different device to attend the talk.
I'm sorry?
So some of us use a separate device to listen to the talk. And so it's actually quite I did it last time and I'm doing it right now to type the link onto a computer where you can run GatherTown. Just a quick feedback on a very minor technical difficulty.
Yeah, so how would you suggest, I mean, you can also get the link if you just register on the website.
Oh, okay, that's how the others manage it.
But let me email it to you right now, though.
Sure.
Oh. Okay, and I guess I'll leave the Zoom open for a little while, so.
Right. Is it the
people
same
can-
link every colloquium?
Yeah, it is. It is. Yes.
Okay.
Yes,
So
yes.
then I just need to get it right once and save
Yeah.
that link somewhere.
Okay. All right.
Sorry
see you
about
there.
the.
Right.
Thanks.
Okay. Bye.
Bye bye.
Okay, so you should have it now.